Okay, so it's a great pleasure to welcome Tapio Schneider and Andrew Stuart, both from Caltech here, to do our first joint seminar. And they will report on their recent research on creating a new data-informed climate model with uncertainty quantification. So please, Tapio.
Yeah, thanks for having us. And yeah, my pleasure to be here. So what Andrew and I will tell you about is indeed what we are doing about building a climate model that learns from data, and that has many aspects, and we'll focus on the learning from data part. What we'll be showing is work where many have contributed, and we'll mention some as we go. I've listed a few of them here, a few of the students and postdoc. I'll show you briefly something on cloud prioritization by Yair Cohen, Ana Yaruga, Jahe, Ignacio Lopez Gomez, and Joey Shen. And then Andrew will talk about some algorithms we use, to which a number of people have contributed, which Andrew will mention as we go. So why we do what we do, I think is pretty clear, and I don't need to spend very much time on it. Earth is warming. Temperatures have risen about a degree on average globally. This is just a map of how this warming was distributed over the last 150 years, just to say that warming is truly global. The gray areas are regions where we don't have enough data to say much. Continents have warmed faster than oceans for reasons we understand. There are interesting areas where there is large natural variability. For example, over the North Atlantic, it's sometimes a bit cooler, sometimes a bit warmer, also a bit cooler in the mid-2010s. But by and large, warming is global, and it's currently quite staggering, actually. I mean, it's about 0.2 degrees per decade now, the rate of warming, and in high latitudes, we had on average already 3 degrees of warming. That's what's happening, and what we not want to know is where we are going, and where we are going is relatively uncertain. It's clear Earth is warming, but how much is unclear. And it's so unclear that planning for it is difficult. Here's just one example of how we quantify how the amount of warming we expect is uncertain. You can just say, suppose we pick a temperature threshold, the 2-degree threshold of the Paris Agreement, and say we don't want to exceed that threshold. So this is 2 degrees warming above pre-industrial times. We already had 1 degree, 1 more degree to go. And you can ask, how much more CO2 can you put into the atmosphere before this additional degree of warming is realized? And in some climate models, you can increase CO2 levels up to close to 600 parts per million. We are at 415 parts per million in the atmosphere. And in other models, this 2 degrees warming is already reached at 480 or so parts per million. And so that's, if we try to translate this into time, 280 parts per million will reach no matter what, no matter, irrespective of policy interventions and the like, within the next 20 years at most. 600 parts per million, even under high emission scenarios, we wouldn't reach for another 40 years or so. So it's a full human generation difference between these two end member scenarios. And there are various factors contributing to these uncertainties. The one that dominates the uncertainties, or the spread among models at least, is how clouds, and especially low clouds, respond to global warming. So the models further on the left on this plot, they're a little less sensitive to global warming, tend to produce more low clouds as the climate warms. The models on the right that are more sensitive to increased CO2 levels, they produce more warming per CO2 increase, tend to produce fewer low clouds as the climate warms. And that's an important feedback, and an important and poorly quantified feedback. Basically, these are the clouds I'm talking about. On the left is stratocumulus clouds. Andrew and I are sitting somewhere around here, California, off the coast. Year round, you have a white blanket of stratocumulus clouds covering the ocean, reflecting sunlight because they're white. And one day when we can fly again and go on vacation, or might fly to the Hawaiian Islands on the right here, you have scattered cumulus clouds around, dark ocean exposed, it's considerably warmer. And fundamentally, we don't know if we get more or less of these stratocumulus clouds or more or less of these cumulus clouds, and that's the dominant uncertainty in climate predictions. More of these low clouds means more white cover, more reflection of sunlight means less warming. Fewer of the low clouds means amplified warming because more dark ocean is exposed. Which way it goes is uncertain. Even the sign of this feedback is uncertain. The magnitude even more so. So that's the dominant uncertainty, and it's just one of several factors that are uncertain. What most of them have in common are that they're either so small scale we cannot resolve them in a climate model, or we don't even know the equations of motion governing them. And the equations governing them, for example, for the land biosphere, the equations are often unknown. And we need to plan for the future that's coming, and we would like to do so rationally and cost effectively. And that means we need better predictions. So how can we make progress? What we set out to do, and we here is, the ideas really started in conversations with Andrew and grew into a larger group over time, and out of which grew this Climate Modeling Alliance, CLIMA. The core idea was that we have a lot of data about Earth. It's about a terabyte per day of data that we receive about Earth from satellites, from ground observations, from ocean floats, gliders, and the like. This is just one example here, the so-called A-train of satellites. Several of them invented, operated by Caltech, JPL, OCO2 in front, for example. It's measuring carbon dioxide, or CloudSat Calypso measuring clouds from space. And we have these data, but the data are not used to the extent that they could be used. They're used for model evaluation, but they have only to a very limited extent been used to calibrate climate models. The main data that have been used to calibrate climate models are energy flux data at the top of the atmosphere. But details about clouds, about the temperature structure and the like have not been used in any systematic way to calibrate climate models. Climate models are hand-tuned to a small set of the data. So we have observational data, and we have the capability of simulating clouds and several other small-scale processes in limited areas. This is a large eddy simulation of a cumulus cloud field, and it is modeled after a field campaign. We can compare this simulation quantitatively with field data, and it matches field data way well. We know that these are good simulations that look pretty. Blue here is rain, gray is the cloud, and the colors at the bottom is the buoyancy field or the temperature field of the surface. So we have these simulations. We know they're quite good. There's no way to be able to scale them up to the globe. If you would like to run these simulations on the globe, you would need a computer about 10 to 11 times faster than the fastest we have. That's not going to happen anytime soon, but we are able to run simulations like that in limited areas. So what we are doing is build a model that can A, learn from observational data, and B, can spin out these high resolution simulations to generate simulated data from which the model can learn as well. You can embed these high resolution simulations for clouds just about in a footprint of a coarse climate model grid box. A climate model grid box is typically tens of kilometers on the side, and that's about the domain size that's achievable in these large eddy high resolution simulations. So you can embed one such simulation in a column of a climate model, or you can embed many of them simultaneously in many columns. You can run them in parallel, you can run them in a distributed computing fashion in the cloud, and they're currently doing that. So you can generate relatively large samples of computationally generated data. And the nice thing about being able to do it is that you can do it in any climate that you simulate, including a climate that's warmer, that's different from the present day, which gives you some way of generating a limited amount of data that's simulated. You have to be aware of the limitations, but you can generate them out of the observed sample, and thereby have a data set that provides some guard against overfitting to the currently observed sample of data we have. So what we are doing is building a climate model, and the climate model at its core has traditional process models. So we, for example, developing a land model together with JPL, land hydrology model, river model, and the like, a land biosphere model developed by Christian Frankenberg at Caltech and people at JPL as well. A group at MIT is developing an ocean model, developing an atmosphere model, and these are in many ways recognizable process-based climate model components. And what we want to do is wrap all these physics, chemistry, biology informed models in a layer of data assimilation machine learning tools that Andrew will talk about, to inform them both with Earth observations, where we have them from space, from the ground, from the water, and from high resolution simulations, for example, of clouds or of sea ice or of ocean turbulence that you can spin out of the model. I don't think we have a good name for what we are doing here. Maybe someone can come up with one. It is in some ways data assimilation or machine learning accelerated science. What we mean by it is you use tools from the data sciences to accelerate, in some ways, the scientific process, how it has worked for a long time. It is not deep learning as such. Deep learning rests primarily in over-parameterization. These are data-hungry methods. They lead to challenges with generalization, interpretability. Transparency is important for climate models. You want to trust the model, and it needs to be transparent for you to be able to trust it. And that is, deep learning methods are maybe not ideal for that purpose. If you think about what makes traditional reductionist science work, maybe in a word, it's sparsity of parameterizations that makes it interpretable, makes it generalizable, and we want to use sparse parameterizations and inform them with data to have generalizability and interpretability of what we do. So in some ways, we want to combine both traditional reductionist science with the data science tools where the reductionism reaches its limits. How does this actually work? Let me just give you a very quick summary of one area where we are pursuing this, and that's in modeling clouds. So what we want is a model that has out-of-sample predictive capabilities and is computationally efficient. We want to predict the climate we haven't seen. So we use the known equations of motion where we have them. We have them for all fluid mechanics, as far as we can go to minimize the number of adjustable parameters and avoid overfitting. And then we want to learn about the rest from data. Now, climate data often do not have high temporal resolution. Say polar orbiting satellites just cross the same place on Earth's surface every 10 to 14 days or so. But what they can give us is good time aggregate statistics. So the idea here that we're pursuing is learning from climate statistics, which contrasts from learning from weather states and weather prediction, for example. So you aggregate in time and use statistics aggregate in time to inform the model. That has advantages that Andrew will talk about. It comes with a challenge. It is computationally challenging because it means you need to aggregate statistics from a climate model. They're expensive to run, and so you need fast algorithms to be able to learn from data to inform it in a computationally expensive model from data. How does it actually work? Let me just sketch out very briefly, without much detail, what we do for modeling clouds and turbulence in the atmosphere. In a nutshell, you take the Navier-Stokes equations of motion we have here, and we pursue a conditional averaging approach. So you average them over one distinct subdomain, call it the environment. That the idea is that contains the more isotropic turbulence, and over coherent structures in the flow, coherent updrafts and downdrafts. And outcome, a set of equations, we don't need to go through the details of which, just to say they are sort of familiar continuity equations, mean equations for scalars like the updraft velocity, and covariance equations for things like the turbulence kinetic energy. And as always, you average on the right-hand side what appears are closure terms that need to be closed in some semi-empirical fashion. Maybe what I'd like to draw your attention to is on the left-hand side here are time-dependent terms, memory terms that appear in these equations. That's one thing that's different about our approach. You can use various formalisms to justify their appearance. Moritz-Swansig formalism gives rise to memory terms like that, and then stochastic closure terms that would be on the right-hand side here. The intuitive interpretation is just that you're reaching resolutions in climate models where you begin to resolve deep convective clouds, for example, and at those resolutions, it becomes crucial that there is memory residing at the subgrid scale. You cannot assume that the subgrid scale instantaneously adjusts to its environment. These are the equations. So there are closure terms or closure functions you need to come up with on the right-hand side. For this particular scheme here, which we use for all turbulence clouds, all cloud regimes, in our atmosphere models, there's a few key functions you need to learn about: entrainment, detrainment lengths, that's rates that are interaction terms between subdomains, pressure gradient term, and mixing length appear in, for example, eddy diffusivities that come up. The eddy diffusivities depend on turbulent kinetic energy and the mixing length. What we do in each of these cases is use physical models as far as they can go. For example, with mixing length, there are minimum dissipation assumptions get you very far in coming up with good functions for the mixing length. It's work Ignacio Lopez Gomez has done. For pressure gradients, simple ideas of how a bubble rises in an atmosphere gives you functional forms for what they should look like and the like. But in each one of those functions, there are either scalar parameters left over or entire functions that need to be closed, and those will have to be learned from data. Andrew will talk about the learning from data part. Let me just, maybe as a bit of a teaser, just show how this works in practice. Here is 4 different cloud and boundary layer regimes. A shallow cumulus cloud that shows the water vapor mixing ratio. The solid line in each is a large eddy simulation, and the dashed line is our one-dimensional model reproducing that. This is a polar boundary layer in the upper right showing velocities, where the solid line is a high resolution simulation, shading is a range of other high resolution simulations. Then the dashed and dotted lines are the one-dimensional model at various resolutions. And this is something we're particularly proud of. These are notoriously hard to simulate, intermittent turbulence and stable boundary layers. So we capture this about as well as large eddy simulations. And if you count degrees of freedom, the large eddy simulations here have 2 million degrees of freedom. The dashed lines have somewhere between a few dozen to 128 degrees of freedom. So it's a vastly reduced order model. Bottom left is deep convection, a deep convective cloud, the updraft velocity. The upper panel shows the updraft velocity during cycle evolution. Again, a large eddy simulation, and underneath is the one-dimensional model. The key thing here is that we capture the gradual onset of deep convection, which is something that climate models and weather forecasting models have had difficulties with for decades. And the key to get this right is actually these memory terms that are on the left-hand side. And another piece that's considered hard is stratocumulus top boundary layers, so stratocumulus clouds like off the coast of California here. Black, again, large eddy simulation. The red or orange dots are data from a field campaign. Gray is a range of other large eddy simulations. This is even hard for large eddy simulations to get right. And then blue is our 1D model that also captures this regime quite well. So this is physics-based. These were calibrated with data coming from high-resolution simulations. And the way they were calibrated was done and the way Andrew will describe next. So I'll hand over to Andrew and he'll take you through calibrate, emulate, sample.
Could I just ask people if they would like to, thank you very much, Tapio, ask questions maybe now on your part. So if there are questions, please, you can unmute yourself and ask. Maybe I can ask, I can start with some. So the parameterizations you're looking for, they're all deterministic, they're not stochastic, is that correct?
What I showed you is all deterministic. We want to make it stochastic. We're working on that. It makes physical sense that they're stochastic, but what I showed you was fully deterministic.
Okay, thanks.
The entrainment, detrainment rates are good candidates for stochastic functions.
Further questions now, then Andrew, please start. And I should say, if you have questions in the audience, please type them in the chat and I can then monitor them. So thank you.
Yeah.
You see that okay?
Yeah.
Good, thanks. I'll welcome questions as I go, so please feel free to interrupt. I think the audience is small enough that it's fine to go through chat, but you can just unmute and interrupt. I'm going to pick up where Tapio left off, and then at the end we will come back. Tapio will present application of the methods that I'm describing to learning of parameters in a particular GCM. So the goal of what I'm going to describe is to do parameter estimation combined with uncertainty quantification in the context of models which are expensive, as GCMs are, for example. Noisy, there's a particular reason why noise is important. As Tapio mentioned, we work with time aggregated data. Were we able to aggregate that data over infinitely long time horizons, there would be no noise present in it. But because of aggregation over finite time intervals, we make noisy evaluations of time averages. And the noise represents uncertainty about the initial condition, internal variability. And we develop methods which eliminate this internal variability and enable us to solve a smooth problem. And those are the two main constraints on the parameter estimation and uncertainty quantification: the expense of the mapping from the parameters to the data space and the noisiness of the evaluation because of the way we use time aggregated statistics. So what I'm going to try and do is give you the big picture of the methodology that we use, and that contains 3 components. Calibration of the model, which roughly speaking means a preliminary first guess at finding estimates of the parameters, an emulation phase in which we replace the model, which is an expensive GCM, for example, by a much cheaper machine learned surrogate. And then, and Tapio will describe this at the end, we use that surrogate to perform standard Monte Carlo Markov chain Bayesian inference, which not only helps us to learn the parameters, but does so in a manner that quantifies uncertainty. As Tapio indicated at the beginning of his talk, uncertainty in cloud coverage is a major source of uncertainty in predictions. And so consequently, it's important not only to calibrate parameters, but to make estimates of the uncertainty in the calibrations, and eventually to try and reduce that uncertainty. So that's what we'll get to when we come back to Tapio at the end of my slides. So I'm going to try and describe this in a very neutral fashion, and model neutral, because there are many places in which parameter estimation play a role. If you want to be concrete, think of G as being a GCM in which parameters theta that we wish to calibrate appear through, for example, a subgrid scale model of clouds. So theta are parameters entering the subgrid scale model. G is the GCM which takes the subgrid scale model as part of its definition. And Y is the data available to us from running the GCM at these parameters. And our objective is to learn the parameters theta from the data Y, typically in the presence of noise. Right, so this is a standard parameter estimation problem. What makes it specific to the climate setting, and indeed to many other complex models in the physical, biological, social sciences, is that we're interested in calibrating the parameters, but also in learning about uncertainty in them. That means solving the Bayesian inverse problem of the probability distribution of the parameters theta given the data Y. That's the first thing. Secondly, G is expensive to evaluate. Our data is time aggregated. So G at parameter theta, evaluation of G means running a GCM over a time horizon of, say, 10, 50 years, something of that type. So each evaluation of G is expensive. And thirdly, as I mentioned, were we to have infinite time averages, we would be able to remove the internal variability of the system, but we don't. And so there's an internal variability residual uncertainty in the evaluation of G. And I will show you methods in our UQ and calibration techniques which deal with this fact that G is only available to us approximately through finite time statistics. And as is commonplace in this setting, differentiating G is not possible. So these constraints mean that standard off-the-shelf software to calibrate theta to Y and to do uncertainty quantification for theta given Y does not apply. So let me just highlight the calibration and uncertainty quantification picture and introduce notation that will be useful throughout my slides. Roughly speaking, what we would like to do is find, in calibrating, we'd like to find a value of parameter theta which matches the data. And so I can write down a mismatch between the data Y and the evaluation of the GCM at the unknown parameters theta. And I might wish to minimize this, or I might wish to minimize a regularized version of this, where I penalize large deviations in theta based on some prior knowledge. So that would be a typical optimization approach to the problem. The Bayesian approach, which computes uncertainty, roughly speaking, boils down to probing a probability distribution on the parameters that enter the subgrid scale model, given the observed data Y. And that has the form of being proportional to the exponential of the negative of phi sub r, the objective function which appeared on the previous slide when I talked about optimization. So there's a kind of duality between optimizing and sampling. And the connection is contained in this formula here. So what we're going to do is develop a method that does both calibration through a form of optimization, then replaces G by a surrogate, and on using that surrogate, we will perform fully Bayesian calculations. And the surrogate will make evaluation of G cheap, and so consequently evaluation of this phi sub r will also become cheap. So the basic methodology that I'm going to describe comprises three components: calibration, emulation, and sampling. The first will be an ensemble Kalman-based approach to generating approximate samples, well, I shouldn't even say samples, approximate solutions to the calibration problem. I'll describe how those ensemble Kalman methods work and a little bit of the history of where they come from. As well as providing a first calibration of the model to the data, these ensemble methods provide training points which can be used to emulate the forward model G and replace it by an emulator G super M, M denoting the number of emulation points. The key point here is that the ensemble methods will generate excellent design points for this emulation. So they give us very good choices of data to which we, on the basis of which we train the emulator. And the emulator is far cheaper to evaluate than G. The emulation I'll describe in the talk today is Gaussian process-based, but there are others that could be used. Neural networks, for example. And then we replace the forward model by its emulator, which is much cheaper. And that then enables us to apply the full methodology of Monte Carlo Markov chain to sample the, posterior distribution on the parameter given the data. In this methodology, all of it is potentially provably, rigorously correct in the sense that all of these steps come with theories, so that that provides justification for our approximation of the uncertainty that arises from this methodology. It's also practical because of the steps we've taken to ensure that these can be implemented with noisy, expensive forward models G. So I'm now going to describe how we do each one of these three phases, but I welcome any questions if there are any. Okay, so let me talk first of all about the calibration phase.
Hi, Andrew.
Yes.
Hello. Maybe I have a quick question.
Sure, please.
Would it make sense to incorporate the dynamics in this procedure? So you mentioned you work with aggregate data, time aggregate data.
Yeah, thank you. It's a really good question. There's a trade-off. By aggregating the data, in some sense, we're throwing away information, which might seem counterintuitive. But because of the chaotic nature of the system, working with actual trajectories and trying to fit the dynamics, it comes at a cost of increasing the complexity of the optimization and the sampling problems. And furthermore, it gets tangled up with the question of learning the initial condition. Of course, that's a key thing to do if you are making a weather forecast. But in the context of climate modeling, where we're trying to make predictions about statistical behavior decades from now, we don't really care about the initial condition. So the approach that we have has the advantage, by using aggregate statistics, of enabling us to eliminate the initial condition. And I'll come back to that point when I get some examples at the end.
Thank you.
Thanks.
I had a question also, Isaac held. Could you say a few more words about your choice of cost function or norm, or your choice of variables y? Seems like there's a lot of freedom there.
There is a lot of freedom there. Thanks for that question. So the assumptions in the specific form of this cost function are essentially Gaussian assumptions in two ways. Firstly, the fact that the cost function with respect to the likelihood contribution, the mismatch between the data and the model, the fact that it's this least squares form arises from assuming Gaussian noise on top of the forward evaluation of the model. And it will show you a justification for that being a sensible choice later on. This penalty here, which encodes prior information, also encodes a Gaussian assumption, or a prior Gaussian assumption on what we know about the parameters before starting. Here I've set everything to be mean zero, but in general there would be a mean and a covariance associated with this prior. Here, to be Gaussian often requires a change of variables and working with transformations of the original variables that one has. And that's something that we also do, and I will touch on briefly later on. But the methodologies that I describe are robust to making changes to these assumptions, but they are justified in the ways I've described. Thank you, Isaac. Okay, so let me say something about the calibration phase. The methods we use are ensemble-Kalman based, but I want to distinguish them from ensemble-Kalman filtering as it is used in state estimation, and also from some other ensemble-Kalman methods that are used for solving inverse problems, which inspired the algorithms we use, but are different from them. So I want to give you a brief, just a very brief history of where our algorithms come from and fit into historical methods. So Kalman, in the context of state estimation for linear dynamical systems subject to Gaussian noise, introduced the Kalman filter. And as I'm sure you all know, that this methodology has become widely used for state estimation in nonlinear dynamical systems. And a major part of that success is due to Evanson, who introduced ensemble methods. And in rough terms, ensemble methods are excellent because they obviate the need for computing derivatives, replacing them by differences across the ensemble. And they've been highly successful, although I think it's fair to say that even in state estimation, the theory behind the sense in which they are accurate lags behind their practical use. Now, solving inverse problems using, or parameter estimation using ensemble Kalman methods really took off in the oil industry. And there are two papers here, one by Chen and Oliver and another by Emmerich and Reynolds, which laid the foundations for the use of ensemble Kalman methods in inverse problems. And they took a perspective in which the ensemble Kalman methods are thought of as transporting the prior to the posterior in one time unit. And indeed, you can read about this perspective in work of Sebastian Reich, going back to 2010, which this paper is, and subsequent studies that he has made. So in this use of ensemble Kalman methods to solve inverse problems, one starts at the prior and transports it through the ensemble to the posterior by running the algorithm for one time unit. That's a very rigid construction, and what we're doing is a generalization that builds on that work, but does not transport the prior to the posterior in one time unit. It transports any initial distribution of particles to the posterior at the cost of iterating over a longer time. And there's some of the history of these, where these methods come from. I'll make the slides available to Georg if you put them on the website. You can pursue the references there. The key point about these methods is that they give rise to interacting particle systems where the particles, that is the state of these systems, are parameter estimates, and the right-hand side of these dynamical systems in which the parameter estimates interact, the right-hand side involves evaluation of the GCM, the forward model. The time that appears in these algorithms is an algorithmic time. It has nothing to do with physical time. And indeed, these will be discretized in the algorithmic time to produce iterative methods. Coming back to the question 2 questions ago, all of the physical time dependence is contained in the definition of G, which computes average time statistics from the output of the GCM given input parameter theta. So these algorithms, what I'm showing you may look a long way from ensemble Kalman, but there's a very clear line and derivation that leads to these methods. You won't be able to, if you haven't seen them before, take in the details, and I don't wish you to have to do so. But just to say that this is essentially an optimization method which will perform the task of making, of minimizing this objective function phi sub r that we were talking about in answer to Isaac's question. And by putting this algorithm in a heat bath, one can also, so essentially I've taken the preceding algorithm and I've added noise and damping. One can also create an algorithm which samples the posterior distribution on the parameters given theta, given the data y. There's a lot to understand about why these methods work, but just to give you an insight into why they work, I'm going to take a mean field limit where I imagine that we have a large number, infinite number of interacting particles. And then one obtains what looks like a Langevin equation for the distribution given by e to the minus the objective function phi sub r. But the particles self-interact through their own covariance. And this is what comes from Kalman methodology. There's a lot of really interesting math that goes with this. What I want to convey to you is that by studying this mean field limit, and I've also invoked an approximation. So the beauty of Kalman methods is that they replace derivatives by differences. And if you use that, you get this actual gradient showing up. They are approximated by differences in these methods. And of course, one doesn't either approach the mean field limit. But if you allow me to make those approximations of differences by a derivative and go into the mean field limit, what you see from this methodology is that you get a stochastic dynamical system whose steady states are the Bayesian posterior distribution. The conclusion of that is that when you actually implement this method in practice with a finite number of particles and without invoking the replacing of differences by derivative, you have an approximate set of samples from the Bayesian posterior distribution. Right? So this is a method of approximately, not rigorously, but just in a reasonably sensible, principled fashion, generating approximate samples from the posterior distribution.
Can I interrupt here, Andrew? Sorry for a quick question.
Yes.
Is there any way to control the convergence rate towards this equilibrium solution? I mean, you want to converge there quickly, I guess. So is there a way to control this?
That's a really good question. So the beauty, let me answer it in the linear case when everything I say is provable. In the linear case, the beauty of this method, and it comes from the ensemble Kalman methodology and the preconditioning by the covariance that is an integral part of all Kalman methods. The rate of convergence to the posterior distribution is independent of the posterior distribution in the linear Gaussian case. It's always e to the minus t. And so in some sense, the algorithm preconditions itself to converge at an optimal rate that's independent of any ill conditioning in the objective function phi sub r. So that's provably the case in the linear setting and empirically seems to hold for nonlinear problems. And that indeed is the key to one of the reasons why the ensemble method is so good for parameter estimation. Thanks, Georg. All right, so where we've got to so far, excluding the linear case where one can actually prove that one samples exactly, what we have is a set of, this should say emulate, not sample, sorry. That word in black, sample, should be emulate. What we'd like to do is turn these approximate samples into more accurate ones. And the way we're going to do that is by using Gaussian processes based on the output of the preceding algorithm to learn a surrogate for the mapping, the GCM, which takes the subgrid scale parameters to the data, which is aggregated time information. And there's a long history to the use of Gaussian processes to replace expensive computer models. You can read about Gaussian processes in this beautiful text of Rasmussen and Williams. And there are two really key papers to the study from a statistical point of view of emulators of complex computer models by Sachs et al. And Kennedy and O'Hagan. And with Aretha Teckentrup, we have theory that justifies the use of these surrogates within the context of Bayesian inversion, which is where we'll end up when I return to Tapio's when we return to Tapio's slides at the end. Let me just show you pictorially what does Gaussian process interpolation do. Before you have any data, you have a Gaussian process representation of G, the function you wish to learn. And this is just a cartoon. And the Gaussian process samples will be all over the place. You then pick some design points where you know the value of G. So these would be for us, this axis here would be the theta axis, the input parameters. And this axis here would be the output of the GCM. You pick a few points where you evaluate G, and then you interpolate using what's called Gaussian process interpolation. And with that comes an estimate of uncertainty. A key thing to understand about Gaussian process methods is that the choice of these design points is key to their success. This is a cartoon picture where everything is, a one-dimensional function of one variable. But if you go to more complex functions with more input variables and greater number of output variables, the choice of these points is very, very important. And in summary, the ensemble Kalman methods that I describe give us evaluations of the pairs theta and g of theta, their input parameters, and evaluations of the GCM. They give very well chosen points for the purposes of emulating the GCM. And that then enables us to sample the posterior distribution using fully Bayesian methods such as Monte Carlo Markov chain, but replacing the GCM by this cheap surrogate. And that's key because these sampling methods can take hundreds of thousands of evaluations of the forward model, which would simply not be possible with the GCM, but are possible with the surrogate. And so this brings me to, we'll end up with Tapio showing you this methodology in action on a GCM. I want to show you something I mentioned right at the beginning, which is the source of noisiness in the evaluations of G. So the kind of problems we're looking at, we have a time-dependent dynamical system depending on a parameter theta that we wish to know. And we have what is commonly called in statistics a nuisance parameter, the initial condition. We're not doing weather forecasting. We don't want to know the initial condition. Okay, so that's a fundamental difference from weather forecasting. The data we're given is in the form of a time average of some function phi of the trajectory. And it's a time average over 10 time units, over t time units. And if the system is ergodic, and this is provably the case for the example I'll give next, and empirically the case for many complex chaotic systems, then this time average over time interval of length t will equal the infinite time average, in which crucially the initial condition disappears, plus a Gaussian, right? That's the central limit theorem for chaotic dynamical systems. And we use this, and I'll show you pictorially how this works. I'll start with a simple example of learning the parameters R and B in the Lorentz 63 model based on knowing time averages of the first and second moments of the entire system. So G would be the infinite time average of the statistics of the problem, but we only have finite time averages. And furthermore, the noise is defined through this difference between the infinite time average and the finite time average. So that's only available to us approximately. So what our methodology gives us is this. If we didn't use a Gaussian process, we would have objective functions that look like the blue curve that you see here. And these objective functions get built into the Gaussian picture. And I'm just showing you two sections of them against the two parameters R and B. So as you can just see, if you try and do optimization over a surface that looks like this, you're going to get in trouble. You're going to get stuck in local minima, or if you do Monte Carlo Markov chain to sample posterior distributions using this misfit function, you're going to take an infinite amount of time. What the Gaussian process methodology does for us is it learns a smooth envelope of this objective function, which is the infinite time average, and it equips us with a measure of uncertainty, which is the shaded orange that you see around here. So using that smooth envelope and the measure of uncertainty, we're able to define a Bayesian inverse problem, which is very computable. And we've solved the problem of A, the fact that G is expensive. We've replaced it by a Gaussian process, which is cheap to evaluate. And B, we've got rid of the noise inherent in the data, in the evaluations of G over finite time averages. So we solved two problems, and in doing so, we have introduced a problem which is tractable. So I'm going to hand over to Tapio now, who will show you application of the methodology, closing the loop, on a particular idealized moist GCM, which you see in front of you. So I'll let Tapio take over, but as we exchange who is sharing, I'm happy to answer any questions.
Maybe I can ask a question then. So is implicitly you're assuming that your measures and all depend smoothly on the parameters, right? If you have that kind of central limit theorem, so all the statistics there should depend smoothly on the parameters. That's correct, right?
That is an assumption, and indeed.
And how good is that assumption for?
Yeah. As you know, it's provably true for the Lorentz 63 case,
yes,
on the basis of Warwick Tucker's work. But otherwise, you know, for larger systems like the GCM, we're just relying on the empirical observation that it appears to be the case. You have a lot of experience in this area, and I'd love to know what you think about it. But my experience is that higher dimensional systems have much greater robustness with respect to parametric dependence of the invariant measure and statistics than do low dimensional ones. Yes. But that's purely empirical, and I don't think we'll ever be at a point where those things are proved in my lifetime for high dimensional problems like Navier-Stokes equation.
Yeah.
Okay, let me just give a quick example. The example is quite simple in that the parameter space is only two-dimensional. It is sort of the downside that it can't show off the high-dimensional scalability of the methods that Andrew described, but the upside is that we have brute force means of computing solutions to just verify that we are doing is correct. This is a very idealized general circulation model. It's a 3D model, but it's statistically is only symmetric and quite simple in many other ways. So it's a model that a number of people have used. Jürgen Frierson, we've used it in my group for a number of years for just studying large-scale dynamics. And it has a convection scheme that depends on two key parameters. There are more parameters than two, but there are really two that matters. One is the relative humidity, this RHREF here, and the time scale tau. So what this convection scheme does is whenever the atmosphere is unstable with respect to moist convection, it relaxes the atmosphere towards a moist adiabat, that's this reference temperature profile, with a fixed relative humidity, and that's this relative humidity parameter. It's a convection scheme of the kind that was used in models maybe 20 years ago. These same schemes aren't really in use anymore, but it serves to illustrate the purpose of what we want to do here. So we have two parameters in this scheme that we want to estimate, the time scale and the reference relative humidity. And Isaac's question about the objective function, the objective function is subjective. You need to use your knowledge of the system here to decide what it is you want to optimize, what you think is informative about the parameters. In this case, it was relatively easy. We do know that, for example, the relative humidity in the mid-troposphere is informative, especially in the tropics, about the relative humidity parameter. The precipitation extremes are informative about the time scale that enters here, and that's what we picked in the objective function here. So the objective function has three physical quantities: the relative humidity, the mean precipitation rate, and a measure of precipitation extremes. More precisely, it's the probability of exceeding a high threshold of precipitation rate that's latitude dependent. So the model is statistically zonally symmetric. So all statistics only depend on latitude, and each one of these is basically a function of latitude. So it's a low resolution model. We have, in the end, an objective function that has 96 terms, three physical quantities with 32 terms each. And here is our initial ensemble that encodes the prior information we gave this, the 100 particles here, 100 ensemble members. The relative humidity scatters between 0 and 1. It's just constrained to be between 0 and 1 at this time scale. The true value is 2 hours. The true value for the relative humidity in this perfect model scenario is 70% at the crosses of the red lines. This timescale scatters quite widely in this timescale space as well. And here is ensemble Kalman inversion, one of the variants of Kalman methods we used. If you let it go, in about 5 iterations, it converges. So it finds the approximately correct parameters quite reliably in a few iterations. So you have 5 iterations, ensemble size 100. You have 500 evaluations of the model that gives you approximately the right parameters in this case. On these 500 evaluations, 500 runs of the climate model, we train again the Gaussian process emulator. And here are the terms in the objective function and its emulator. So here's the relative humidity as a function of latitude. It's in a mid-troposphere, the mean precipitation rate. And what we picked for the extreme precipitation statistics is the frequency of exceeding a high threshold, and the threshold is picked as the 90th percentile at each latitude, should be exceeded 10% of the time, which is why these values cluster around 10%. Then the blue whiskers give the internal variability here from the climate model. It's just the, I believe it was 90% confidence interval. And the orange shading shows the Gaussian process emulator and its uncertainty. And the key is that the Gaussian process emulator captures the objective function very well. And crucially, it captures the dependence of the objective functions on these 2 parameters we have in the problem also quite well. If you want to go to higher dimensional problems, Andrew mentioned that neural networks, for example, might be better for emulation because they scale better to higher dimensions, and Gaussian processes do. But in principle, all these methods should scale well to high dimensions. And we have some examples in prototypes where we can show that. Now, if you zoom in at the last iteration here, this is this 2-dimensional parameter space again, time scale, and the relative humidity. The black dots is the Kalman ensemble. You see it's not quite a point, but it's a very narrow cloud of points. And the shading now is the posterior that you get after Markov chain Monte Carlo sampling from the emulator. There's 500,000 iterations of MCMC performed on the emulator, so they're very fast to do because the emulator is very cheap to evaluate. And the key thing is that the spread, say the standard deviation in either one of the parameters of the posterior is about an order of magnitude larger than the spread in the end that the Kalman ensemble gives you. So the Kalman ensemble collapses to a point, it calibrates the parameters relatively well, but it does not give good uncertainty estimates. The sampling from a posterior does, and this model is simple enough that we can do brute force sampling on the model to evaluate something that Andrew called the Goldish standard for this standard for the uncertainty. It's only Goldish and not Gold because that in itself has problems with internal variability that Andrew mentioned. So MCMC gets stuck in minima from internal variability. And it's not easy to come up with a true gold standard there. But this Goldish standard is roughly consistent with what the, say, in a standard deviation of statistics, what the emulator gave us, which is to say, this emulator gives us good Bayesian inversion, good Bayesian learning of these parameters with good uncertainty estimates at about 1,000th of the cost what Markov chain Monte Carlo would cost on this climate model, because the emulator is basically free to evaluate, and we only needed about 500 evaluations of the model to get all of this. So there's a paper submitted with this proof of concept. I'll also post the slides. There's an archive link down there. Ollie Dunbar is the first author on that one. Once you have parameters with quantified uncertainties, you can draw from the posterior for the parameters to produce climate predictions with quantified uncertainties. Here's just one example. We simulated a warmer climate, and we know that precipitation extremes become more frequent in the warmer climate. So this is the same exceedance over the threshold that we had before, the same threshold in a control climate, which, this is the probability of exceeding 99.9th percentile of control precipitation in a warmer climate. So that probability increases in a warmer climate. You get to 3% or so at the poles here, above 1% in mid-latitudes. And the shading gives you the uncertainty on this prediction. The uncertainties here have a shape that's understandable to us and in some ways well known. They're much larger in the tropics, which is fairly typical for what you see in climate models. They're smaller in mid-latitudes. And now we have the quantification of the parametric uncertainty. What you like to have too is, of course, structural model errors quantified. And that's something we're working on with one postdoc in particular who's working with Andrew Mead and Long Wu. There's a paper with the concepts on how to do this, also submitted. The key, let me just say this, if you want to learn structural model error, one key is what we call the do no harm principle. You don't want to learn a model error just because you have no information otherwise. So you just learn a model error just simply because that's consistent with data in places where the model error can be non-zero simply because data are constrained to be zero. So what you want is model errors to be sparse functions. They should be zero unless data force them to be non-zero, and that's a key piece of this paper that Jin Long wrote on sparse learning with the common methods. So we're working on using this in other areas of modeling, the land model now. I already showed some examples from the convection scheme, the turbulence convection scheme. The objective function there looks a bit different and contains things like the liquid water path and the profile of moisture in the atmosphere, all things that are measurable in principle and that we use to calibrate the model, in that case with large eddy simulations. So again, what we're doing is build a climate model that uses these tools, data assimilation, machine learning, to inform all model components. We have prototypes now for various parts of it. The MIT group, for example, has been showing how to use these methods for calibrating convection parameterizations for an ocean model. It is beginning to do this with a land hydrology model, with a land biosphere model. It's also starting. What we want to do in the next few years is build a model that jointly learns from data, where all these components are jointly informed with data. Right now, we are doing this piece by piece. In the end, we want to put it together and have the models learn jointly from data. And what that will give you is, once you have quantified uncertainties for the joint components, you have posterior densities for joint parameters, and you learn about compensating model errors, for example. You can analyze that after the fact to learn about where there are compensating model errors that you've made, and can use that to refine the process models, for example. I want to see that we get improved climate simulations of the present climate. At first, out of it, things like rainfall distribution, rainfall extremes, cloud cover. The indication of the cloud cover is, from what we have so far, we're doing pretty well, and we'll see how well it really works once you put it together in a global model. And we want to provide predictions with quantified uncertainties, including quantified structural errors, where the uncertainty quantification is based on the available Earth observations and high resolution simulations that, for example, of clouds or ocean turbulence and the like. That's where we are. Lots of things to be done. Let me just maybe summarize a few key points. I think it's clear that reducing and quantifying uncertainties both is important in climate models, and it's urgent. And we think it's within reach. It's not easy, but it can be done. And our approach is to basically combine standard science, as it always has been done, with data-driven approaches that exploit climate statistics for the reasons that Andrew described. And I showed just a teaser of some results of these physics-based subgrid scale models for turbulence and clouds. It's one unified scheme that seems to work for a range of cloud and turbulence regimes that have vexed climate models for decades. It works well, and I should say it has 9 parameters. What I showed you, it's very sparsely parameterized, and we have hope that this will generalize well, and we'll see how well it works in a global model. These various subgrid scale models we have for land, atmosphere, ocean, and so forth, they'll learn both from observations and where you can have them high resolution simulations that you can spin out on the fly. And this calibrate, emulate, sample family of algorithms is forming the core of the data assimilation machine learning pipeline. It's about a factor 1,000 faster than traditional Bayesian learning algorithms, because the emulator is very fast to evaluate, and the many evaluations that you would usually need to do are done with the emulator, which cost essentially nothing compared with running a climate models. There's a lot of work ongoing and still to be done on other subgrid scale models. We're working on other filtering strategies. The questions of how to optimally target high resolution simulations, where do you put them to be most informative, which can be incorporated into the calibrate, emulate sampling pipeline. Ollie Dunbar is working on it. Many other things remain to be done, and we welcome people to join us. I think there's a lot of exciting science happening, and we hope it will result in ultimately better climate predictions and better climate models. Yeah, happy to answer more questions and leave it at that. Thank you.
Well, thank you very much, both of you, for fantastic, fascinating talk. This is very impressive to build this. Are there questions? I will, maybe if I stop the recording, people feel more comfortable asking questions. I definitely have some, so I'll stop the recording now.